You know, there's something rather extraordinary about Neptune that I think most people don't fully appreciate, something that makes it one of the most hostile environments in the entire solar system, and that's the wind. Neptune has the fastest winds in the solar system, sustained winds exceeding 2,000 kilometers per hour, nearly twice the speed of sound on Earth, winds so powerful and so relentless that they make Earth's most violent hurricanes look gentle by comparison. And I want to explore why these winds exist, what they would do to anything encountering them, and why I think it's genuinely impossible for any spacecraft or probe or human-made object to survive for any meaningful length of time in Neptune's atmosphere. Not difficult, not just extremely challenging, but genuinely impossible with any technology we can currently envision or are likely to develop. Because Neptune's winds aren't just fast, they're fast in an environment that's already extraordinarily hostile in multiple other ways. The combination of extreme wind speeds with crushing pressures, with temperatures near absolute zero, with an atmosphere of hydrogen and helium and methane that's completely alien to Earth-based materials and engineering. This combination creates conditions that are, I believe, fundamentally unsurvivable for any technology we know how to build. Let me start by giving you some context about Neptune itself, because I think understanding the planet as a whole helps explain why the winds are so extreme and why the environment is so hostile. Neptune is the 8th and outermost planet in our solar system, orbiting at an average distance of about 5 billion kilometers from the Sun, roughly 30 times farther from the Sun than Earth. It's an ice giant, the smaller twin of Uranus, with a mass about 17 times Earth's mass, but a radius only about 4 times Earth's radius, which means it's tremendously dense compared to the gas giants Jupiter and Saturn. Neptune is cold, extraordinarily cold. The average temperature in the upper atmosphere is about minus 200 degrees Celsius, or 73 Kelvin, just 73 degrees above absolute zero. This is cold enough to freeze almost any substance into solid form, cold enough that conventional materials become brittle and fail, cold enough that the atmospheric gases behave in ways quite different from how they behave in Earth's temperate atmosphere. And Neptune is dark. At 30 times Earth's distance from the Sun, it receives only about 1/900th of the sunlight that Earth receives. It's perpetually in twilight at best, with the Sun appearing as just a very bright star rather than a disk, providing minimal heat and minimal light. This lack of solar heating makes Neptune's powerful winds particularly puzzling, as I'll discuss. Neptune's atmosphere is primarily hydrogen and helium, like Jupiter and Saturn, but with a significant amount of methane, about 2% by volume, which gives Neptune its characteristic blue colour. Methane absorbs red light, so the planet appears blue in photographs. Below the visible atmosphere lies a mantle of water, ammonia and methane ices, not solid ice as we know it, but hot ice that remains in liquid or superionic states despite being called ice, due to the tremendous pressures deeper in the planet. And at the centre is a rocky core, probably about the mass of Earth, where pressures reach millions of atmospheres and temperatures reach thousands of degrees Kelvin. But it's the atmosphere we're concerned with here, and specifically the winds. Neptune's winds were first discovered by Voyager 2, which flew past Neptune in August 1989, the only spacecraft ever to visit the planet. Voyager 2's observations revealed enormous storm systems, including the Great Dark Spot, a storm system similar to Jupiter's Great Red Spot, but shorter-lived and measured wind speeds that shocked planetary scientists. The fastest winds measured were in the southern hemisphere, where speeds reached approximately 2,100 kilometers per hour, about 580 meters per second. For context, that's about 1.7 times the speed of sound in Earth's atmosphere at sea level. It's faster than the speed of sound in Neptune's atmosphere as well, which means these are supersonic winds, creating shock waves as they blow. It's about 5 times faster than the fastest tornado winds on Earth. It's roughly the speed of a rifle bullet. And these aren't brief gusts, these are sustained winds that blow continuously for years or decades, reshaping Neptune's cloud formations, driving enormous storm systems, creating conditions of constant, unrelenting violence across the entire planet. Now, why does Neptune have such extreme winds? This is actually a puzzle that planetary scientists don't fully understand, because the energy required to drive such winds is enormous, and the obvious energy source, solar heating, is minimal at Neptune's distance. On Earth, winds are driven primarily by differential solar heating. The sun heats the equator more than the poles, creating temperature gradients that drive air circulation. But Neptune receives so little solar energy, about 900 times less than Earth per unit area, that solar heating alone cannot explain the violent winds. The answer appears to be that Neptune has a significant internal heat source. The planet radiates about 2.6 times more energy than it receives from the sun, which means it's generating heat internally through some process, probably gravitational contraction, the slow settling and compression of material in the planet's interior, releasing gravitational potential energy as heat. This internal heat released from below creates temperature gradients and instabilities in the atmosphere that drive circulation and wind. But the details of how this works, why Neptune's winds are so much faster than winds on other planets with internal heat sources, remain uncertain. What's clear is that Neptune's atmosphere is tremendously dynamic and violent, constantly churning with energy, with massive storms forming and dissipating, with cloud bands racing around the planet at supersonic speeds. And this brings me to the central question. What would happen to a spacecraft or probe that tried to enter Neptune's atmosphere and survive long enough to make measurements or explore? Could we build something capable of withstanding these conditions? I'm going to argue that the answer is no, that the combination of extreme winds with other hostile environmental factors makes survival essentially impossible. Let me start by talking about what 2,000 km/h winds actually mean in terms of forces and stresses on an object. Wind doesn't damage things through its speed alone, it damages things through dynamic pressure, which is the force per unit area exerted by moving air on a stationary object. The dynamic pressure is proportional to the density of the air and to the square of the wind velocity. At Neptune, in the upper atmosphere where these extreme winds occur, the atmospheric density is very low, much lower than Earth's sea level density. At the altitude where winds are fastest, perhaps around the 1 bar pressure level, the density is roughly comparable to Earth's stratosphere, perhaps 1-10th or 1/20th of sea level density. So let's do a rough calculation. Dynamic pressure is given by Q equals half ρ squared, where ρ is density and v is velocity. If we take ρ is approximately equal to 0.1 kilograms per cubic meter, roughly 1/10th of Earth's sea level density, and v is approximately equal to 600 meters per second, about 2,100 kilometers per hour, then Q is approximately equal to half times 0.1 times 600 squared is approximately equal to 18,000 pascals, or about 0.18 atmospheres. For comparison, hurricane force winds on Earth, say 50 meters per second, create dynamic pressures of about half times 1.2 times 50 squared is approximately equal to 1,500 pascals at sea level. So Neptune's winds, even in the thin upper atmosphere, create dynamic pressures about 12 times greater than hurricane force winds on Earth. And as a probe descends deeper into Neptune's atmosphere, into regions of higher density, the dynamic pressure increases proportionally, even if wind speeds remain constant, which they might not. Winds might be even stronger at depth. Now, 18,000 pascals might not sound like much, it's only about zero. 18 atmospheres, about the same as a stiff breeze on Earth creates against your hand. But remember, this pressure acts on every surface exposed to the wind, and it acts continuously, relentlessly, hour after hour after hour. And more importantly, the pressure isn't uniform. It creates turbulence, buffeting, vibrations, fluctuating forces that stress materials and structures in complex ways. Let me try to give you a sense of what this means practically. Imagine a spherical probe, say 1 meter in diameter, descending into Neptune's atmosphere. The cross-sectional area exposed to the wind is about 0.8 square meters. At a dynamic pressure of 18,000 pascals, the total force on the probe is about 14,000 newtons, or roughly 1,400 kilograms force, equivalent to having a small car pushing against the probe continuously. This force wants to accelerate the probe downwind, wants to drag it along with the wind. If the probe has any irregularities, antennas, instruments protruding from the surface, any non-spherical features, those create additional drag and stress concentrations where forces are higher. Antennas would be bent or ripped off. Instrument booms would be broken. Any parachute or drogue used to slow descent would be shredded instantly. Conventional parachutes simply cannot survive these wind speeds and dynamic pressures. But the force itself isn't the only problem, or even the main problem. The bigger issue is turbulence and vibration. Wind at these speeds is never smooth and laminar. It's chaotic, turbulent, full of eddies and vortices and shock waves. The probe would be buffeted constantly, experiencing rapidly fluctuating forces from all directions, shaking and vibrating at frequencies that could induce resonances in structural components or fatigue in materials. Over time, and we're talking about hours or days of exposure, this constant vibration would cause fatigue, failures, welds would crack, joints would loosen. Materials would develop fractures that propagate until components fail. Even if the probe is initially strong enough to withstand the average forces, the cyclic loading from turbulence would eventually cause structural failure. And there's another effect that's particularly destructive at supersonic speeds: shock waves and aerodynamic heating. When an object moves through a fluid at supersonic speeds, or equivalently, when supersonic winds blow past a stationary object, shock waves form. These are discontinuities where pressure and temperature jump suddenly, and they create additional heating and stress on surfaces. At 600 meters per second, about Mach 1.7 inches Neptune's atmosphere, shock waves would form around any probe, heating surfaces through compression and friction. Now, you might think that heating isn't a concern in an environment that's minus 200 degrees Celsius, that any heat generated would be quickly dissipated into the cold surroundings. But aerodynamic heating depends on wind speed and doesn't care about ambient temperature. At high speeds, friction and compression heat surfaces regardless of how cold the surrounding air is. The heating isn't as severe as during Earth atmospheric re-entry, where speeds are 7 to 8 kilometers per second, but it's still significant. Surfaces exposed to supersonic winds could heat by tens or hundreds of degrees above ambient, creating thermal stresses as different parts of the probe heat at different rates. And the combination of extreme cold with localized heating creates particularly severe thermal stress. Materials contract when cold and expand when hot. If a probe is at minus 200 degrees Celsius, but its windward surface is heated to minus 100 degrees by aerodynamic friction, that creates enormous thermal gradients and stresses that can crack materials or cause components to separate. So the wind alone, just the mechanical and thermal effects of 2,000 km per hour winds, would be extraordinarily destructive. would subject any probe to forces and stresses and vibrations that would likely cause failure within hours or days, even with robust engineering. But the wind isn't the only challenge. Let me talk about pressure, because as a probe descends into Neptune's atmosphere, seeking to explore deeper regions where conditions might be more interesting scientifically, it encounters exponentially increasing pressure that creates its own set of insurmountable challenges. Neptune's atmosphere, like any atmosphere, increases in pressure with depth, according to hydrostatic equilibrium. Pressure increases exponentially as you descend because you have more atmosphere above you pressing down. The pressure we usually reference for planetary atmospheres is the 1 bar level, the altitude where atmospheric pressure equals Earth's sea level pressure. On Neptune, this is defined as the 0 altitude reference point, though of course Neptune has no solid surface, so altitude is somewhat arbitrary. As you descend below the 1 bar level, pressure increases rapidly. At 10 bars, about 10 atmospheres, you're only perhaps 50 to 100 kilometers deeper. At 100 bars, you're a few hundred kilometers deeper. At 1,000 bars, roughly 15,000 pounds per square inches, about twice the pressure at the deepest parts of Earth's oceans, you're perhaps 500 kilometers below the 1 bar level. And pressures continue increasing with depth. Eventually, at thousands of kilometers depth, you reach pressures of millions of atmospheres, where the hydrogen atmosphere transitions into exotic high-pressure phases and eventually into the ice mantle. Now, designing equipment to withstand high pressure is certainly possible. We've built submersibles that can reach the deepest parts of Earth's oceans, withstanding pressures of about 1,100 bars. We've built pressure vessels for industrial applications that can handle thousands of bars. So pressure alone, whilst challenging, is not necessarily impossible to engineer for. But here's the problem. You need to engineer for pressure and wind simultaneously, and these requirements conflict. To withstand high pressure, you want thick-walled, heavily reinforced structures, pressure vessels, with small openings and massive structural support. But thick-walled structures are heavy, and heavy structures are difficult to insert into planetary atmospheres because they require more energy to slow down during entry, and they create more heating during entry. Moreover, thick-walled structures have more mass, which means more inertia, which means the same wind forces create larger accelerations and stresses. And there's a more fundamental conflict. To make scientific measurements, a probe needs instruments exposed to the environment, sensors measuring temperature, pressure, composition, wind speed. These instruments need to be in contact with the atmosphere, which means they can't be fully enclosed in protective pressure vessels. They're vulnerable to the wind, to the turbulence, to the extreme conditions. How do you protect them while still allowing them to function? On Earth's ocean floor, where pressures are comparable to Neptune's deeper atmosphere, we can build robust instruments because they only need to withstand pressure, not violent winds. The ocean floor is relatively calm. There are currents, certainly, but nothing like supersonic turbulence. Neptune's atmosphere combines the worst of both worlds, crushing pressure and violent winds simultaneously. And then there's temperature, which I've mentioned but want to explore in more detail because extreme cold creates its own set of challenges that compound the problems from wind and pressure. At minus 200 degrees Celsius, materials behave very differently than they do at room temperature. Metals become brittle, their crystal structures change in ways that reduce ductility and increase the probability of fracture. Plastics and rubbers become hard and inflexible, losing their ability to seal or flex. Lubricants freeze or become viscous, causing mechanical systems to seize. Electronics malfunction as semiconductor properties change with temperature. Batteries lose capacity or stop working entirely as electrolyte freezing or sluggish chemistry prevents current flow. And thermal contraction causes dimensional changes. Materials shrink as they cool, and different materials shrink by different amounts, creating stresses at joints and interfaces that can cause separation or cracking. We do have experience with operating equipment in extreme cold. Antarctic research stations operate at temperatures down to minus 90 degrees Celsius. Spacecraft operate in environments that reach minus 200 degrees Celsius or colder. So engineering for cold is possible, but again, it's the combination that's deadly. You need materials that remain ductile at minus 200 degrees, while also being strong enough to withstand supersonic winds and high pressures. You need seals that remain flexible in extreme cold, while also being robust enough to maintain pressure, integrity. You need electronics that function at cryogenic temperatures while also being compact and lightweight enough to fit in a probe that must be small enough to be delivered to Neptune. These requirements increasingly constrain your design options until you're left with very few materials and approaches that might work, and even those face severe challenges. For instance, titanium alloys are strong, relatively lightweight, and maintain ductility at cryogenic temperatures, making them good candidates for Neptune probe structures. But titanium is difficult to machine and weld, is expensive, and has lower strength to weight ratio than some other materials. And no material is perfect. Every choice involves compromises. Now let me talk about a challenge that's more subtle, but equally important: the chemical environment of Neptune's atmosphere. Neptune's atmosphere is primarily hydrogen and helium, but it also contains methane, ammonia, hydrogen sulfide, and various hydrocarbons formed from methane photochemistry in the upper atmosphere. And some of these compounds are chemically reactive, particularly at the temperatures and pressures found in Neptune's atmosphere. Hydrogen itself, under certain conditions, can be problematic for materials. Hydrogen embrittlement is a phenomenon where hydrogen atoms diffuse into metal crystal structures and reduce ductility, making materials more prone to cracking. This is typically a problem at high temperatures and pressures, and it's not clear how significant it is at Neptune's cold temperatures, but it's a potential concern for long-duration exposure to hydrogen-rich atmospheres. So we'd established that Neptune's winds create dynamic pressures far exceeding anything on Earth, that the combination of supersonic speeds with extreme cold and increasing pressure creates an environment that's extraordinarily hostile to any engineered system. But I want to continue now by exploring what would actually happen to a probe during descent into Neptune's atmosphere, the cascade of failures and challenges that would occur, and why I think the entire enterprise is fundamentally impossible with any technology we can realistically develop. Let me start by thinking through what a Neptune atmospheric probe mission would actually look like, because understanding the mission profile helps clarify why survival is so difficult. You can't simply fly a spacecraft directly into Neptune's atmosphere at interplanetary velocities. You'd burn up instantly from the tremendous heating. So you need to slow down first, either by using rocket propulsion to reduce your velocity before atmospheric entry, or by entering at a very shallow angle and using the upper atmosphere to gradually slow down over multiple passes. Both approaches have severe problems. Using rocket propulsion to slow down before entry requires carrying enormous amounts of fuel. The velocity change needed is several kilometers per second, and the rocket equation tells us that achieving large velocity changes requires exponentially more fuel. This makes the spacecraft tremendously massive and expensive. Then you still need to deliver that massive spacecraft to Neptune, which itself requires years of flight time and more fuel for trajectory corrections. The alternative error capture, using atmospheric drag to slow down, is theoretically more efficient but requires surviving multiple passes through Neptune's outer atmosphere while experiencing tremendous heating and dynamic pressure. And remember, even the outer atmosphere has those supersonic winds, so you're not just dealing with the heating from your own velocity, but also with buffeting from winds blowing at different speeds and directions at different altitudes. Let's say you somehow solve the atmospheric entry problem. that you've slowed down enough to deploy a probe that will descend through the atmosphere making measurements. What happens next? Initially, in the very upper atmosphere, conditions are relatively benign. Pressure is low, temperature is cold but manageable. Winds exist, but the low density means dynamic pressures are modest. The probe might survive this phase for hours, descending gradually, making measurements of atmospheric composition and temperature and pressure as it falls. But as it descends, conditions deteriorate rapidly. Wind speeds increase, or at least remain very high. Atmospheric density increases exponentially, which means dynamic pressure increases exponentially, even if wind speed stays constant. Temperature might increase slightly as you descend and get closer to the internal heat source, but it remains well below freezing. And pressure increases exponentially, doubling every certain number of kilometers of altitude drop. Let me try to estimate how long a probe might survive. Let's say the probe is robust, well engineered, using the best materials we can devise. Let's say it's spherical to minimize drag, heavily reinforced to withstand pressure, equipped with heaters to prevent electronics from freezing, with instruments designed to function in extreme cold. In the upper atmosphere, at low pressures and moderate dynamic pressures, it might survive indefinitely, hours, days, possibly longer. But as it descends into denser regions, as dynamic pressure increases, as turbulence becomes more violent, structural stresses accumulate, fatigue damage grows, small cracks propagate. Seals begin to leak. After some period, let's say optimistically, it's 10 hours, perhaps even 20 hours if engineering is superb, something fails. Maybe a seal ruptures from the combination of pressure differential and vibration. Maybe a structural member cracks from fatigue. Maybe an antenna or sensor boom breaks off from wind stress. And once one failure occurs, it often triggers a cascade. A seal rupture allows atmospheric gases to enter the probe's interior. If the interior was maintained at low pressure to reduce structural stress, the pressure equalization creates forces that damage other components. If the interior was pressurized to protect electronics, the incoming atmosphere might be chemically reactive with interior materials, or might freeze and damage components. A structural crack propagates rapidly once it reaches a critical length, particularly under cyclic loading from turbulence. The structure weakens, deforms more under wind stress, which increases drag and dynamic pressure, which accelerates the failure. Within minutes or hours of the first failure, the probe is likely non-functional, structurally compromised, electronics damaged by pressure or chemical contamination, no longer able to transmit data or make measurements. It becomes just debris tumbling through Neptune's atmosphere, continuing to descend until it reaches depths where pressure is so enormous that it's crushed completely, or until it eventually settles into the deep interior where materials melt or dissolve in the exotic high-pressure fluids. So I would estimate that even a well-designed probe might survive 10 to 20 hours in Neptune's atmosphere before catastrophic failure. That's not very long, not long enough to explore the full depth of the atmosphere, not long enough to study long-term atmospheric dynamics, not long enough to make comprehensive measurements of Neptune's interior structure. And 10 to 20 hours is optimistic. More realistic estimates, considering all the challenges, might be just a few hours, or even less. But let me think about whether there are any design approaches that might extend survival time, any clever engineering solutions that could overcome these challenges. What if we made the probe much smaller? Small things have advantages in extreme environments. They have less mass. So wind forces create smaller absolute stresses. They have less surface area relative to their structural elements, so they can be proportionally stronger. They have shorter thermal equilibration times, so temperature gradients are less severe. But small probes also have disadvantages. They have less volume for scientific instruments, less power generation capacity, less ability to carry robust structures and redundant systems, and crucially, they're harder to communicate. With a small antenna, has less gain, requires more power to transmit given distance, receives weaker signals. And from Neptune, you're trying to communicate across billions of kilometers to Earth. The signal is already extraordinarily weak. Making the probe smaller makes communication even more difficult or impossible. What if we made the probe much larger? Large size has advantages: more volume for instruments and structural reinforcement, more power generation capacity, more redundancy. But large size also means more mass, which means more difficult and expensive to launch and to deliver to Neptune. And more mass means more momentum, which means larger forces from wind deceleration, which means greater structural stresses. And a larger cross-section means more absolute force from wind, even if pressure is the same. So I don't think there's an optimal size that solves the problem. Small or large, you face severe challenges. What if we made the probe extremely robust, massively over-engineered for strength? Use thick titanium or steel pressure vessels, heavy structural reinforcement, redundant systems, conservative design margins. This would certainly extend survival time. A more robust probe would take longer to fail from fatigue and stress. But the engineering penalties are severe. A massively robust probe is tremendously heavy, which makes it expensive to launch and difficult to slow down for atmospheric entry. And eventually, even the most robust probe fails. You can delay failure, but not prevent it indefinitely. Moreover, heavy probes sink faster through the atmosphere, spending less time at each altitude level, which reduces the scientific value of the mission. So massive robustness helps, but doesn't solve the fundamental problem. What if we used active systems to counteract the wind? For instance, what if the probe had thrusters that could fire to stabilize it against buffeting, to maintain orientation, to prevent tumbling? Active stabilization is certainly possible. In principle, rockets do this during atmospheric entry, but it requires fuel, and fuel is mass, and you have limited fuel capacity. For a mission lasting hours in violent winds, the fuel requirements for continuous active stabilization would be prohibitive. You'd need to carry more fuel than the rest of the probe's mass combined, which is impractical. And eventually you run out of fuel and then you're back to passive survival, which fails for the reasons I've discussed. What if we used a different descent strategy? Instead of free falling through the atmosphere, what if we used a buoyancy approach, filling a large envelope with hydrogen so the probe floats at a constant altitude, like a balloon? This would allow you to stay at a chosen altitude indefinitely, avoiding the increasing pressure and density of deeper regions. But hydrogen balloons in Neptune's hydrogen atmosphere provide no buoyancy. You need a gas that's less dense than the surrounding atmosphere. And there's nothing less dense than hydrogen except helium. And Neptune's atmosphere is already a hydrogen-helium mix. So buoyancy doesn't work. You'd need to use heating to create a hot air balloon effect where the gas inside your envelope is less dense because it's hotter than surrounding atmosphere. But maintaining high temperatures in minus 200-degree environment with supersonic winds requires enormous energy. And a balloon envelope large enough to provide significant lift would present enormous surface area to those winds and would be torn apart almost immediately. So I don't see a buoyancy solution. What about using multiple small probes instead of one large probe? The idea being that some might fail but others might survive, giving you redundancy and extended mission lifetime. This is a valid approach for increasing overall mission success probability, but it doesn't solve the fundamental survival problem. Each individual probe still faces the same challenges and has similar survival time. And multiple probes mean more complexity, more mass, more cost. You might get more total data by having 5 probes that each survive 5 hours than by having one probe that survives 10 hours, but you haven't extended individual probe survival time. What if we only targeted the upper atmosphere, staying at low pressures and densities where dynamic pressures are manageable? This is actually the most realistic approach. Design a mission that explores Neptune's upper atmosphere above the 1 bar level, where conditions are less extreme. Voyager 2 made some measurements remotely, and a future orbiter with remote sensing instruments could characterize upper atmospheric composition and dynamics without entering the atmosphere at all. But this doesn't give you access to the deeper atmosphere, to the regions where pressures are high and where the interesting transitions occur, where hydrogen becomes metallic, where ice phases exist, where Neptune's internal structure and energy sources can be studied. The most scientifically interesting regions are precisely the regions that are impossible to access. So when I examine all possible design approaches, all potential engineering solutions, I find that none of them overcome the fundamental challenges. You can extend survival time modestly through clever engineering, but you can't achieve long duration survival days or weeks or months that would be needed for comprehensive atmospheric study. The environment is simply too hostile. The combination of challenges too severe. Now let me talk about something else that makes Neptune atmospheric exploration particularly difficult, and that's communication. Any probe descending into Neptune's atmosphere needs to transmit data back to Earth, otherwise the mission is pointless. You're not gaining knowledge from measurements you can't receive. But communication from Neptune is extraordinarily challenging. First, there's the distance. Neptune is about 4.5 billion kilometers from Earth at its closest approach, and up to about 4.7 billion kilometers at its farthest. Radio signals travel at the speed of light, which means a one-way transmission time of roughly 4 hours. This isn't a fundamental barrier. We can wait 4 hours to receive data, but it means that communication is one way. You can't control the probe in real time, can't respond to changing conditions, can't troubleshoot problems as they occur. The probe must be autonomous, pre-programmed to handle all situations it might encounter. Second, signal strength decreases with the square of distance. A transmission from Neptune is about 900 times weaker than the same transmission from Earth orbit would be just due to geometric spreading. To receive such weak signals requires either very large antennas on Earth, which we have. The Deep Space Network uses dishes 70 meters in diameter, or relatively powerful transmitters on the probe, or both. But power is limited on the probe. You're probably using radioisotope thermoelectric generators, TGs, for power. Since solar panels are useless at Neptune's distance, the sun is too dim. An RTG might provide a few hundred watts of electricity, and only a fraction of that can be devoted to communications. This limits data transmission rates to kilobits per second at best, which means you can only transmit limited amounts of data during the mission. Third, the probe is descending through an atmosphere that contains ionized particles, clouds of various compositions, and complex chemistry. These can absorb or scatter radio signals, particularly at certain frequencies. You need to choose your communication frequency carefully to minimize atmospheric attenuation, which constrains your antenna design and might reduce data rates. Fourth, the probe is being buffeted by supersonic winds, which means its orientation is constantly changing. If you're using a directional antenna to maximize signal strength, which you probably are, to compensate for the huge distance, then maintaining orientation toward Earth is crucial. But maintaining orientation in violent winds is difficult or impossible, as I discussed. If your antenna isn't pointed at Earth, your signal strength drops dramatically, or your transmission is lost entirely. So communication is yet another challenge that makes Neptune atmospheric missions extraordinarily difficult. You need power for communication, you need to maintain orientation, you need to transmit fast enough to send your data before the probe fails, and you need Earth-based receiving systems capable of detecting incredibly weak signals. All of this is technically possible in principle, but adds to the overall complexity and difficulty and cost of the mission. Now, you might ask, haven't we successfully sent probes into other planetary atmospheres? Haven't we studied Venus's atmosphere with multiple probes, including Soviet Venera landers that transmitted from the surface? Haven't we sent the Galileo probe into Jupiter's atmosphere? Doesn't this demonstrate that atmospheric probe missions are feasible even in hostile environments? And yes, these missions have succeeded and have returned valuable data. But the environments are different, and the missions were limited in ways that wouldn't work for comprehensive Neptune exploration. The Venera probes that reached Venus's surface survived for about 23 minutes to 2 hours before succumbing to the extreme heat over 450 degrees Celsius and crushing pressure about 90 bars. They were heavily armoured pressure vessels, tremendously robust but also tremendously heavy, and they succeeded in part because Venus's atmosphere, whilst hot and high pressure, doesn't have supersonic winds. Conditions are extreme but relatively static. Once you're on the surface or descending at low velocity, you're not facing violent buffeting. The Galileo Jupiter probe descended into Jupiter's atmosphere for about 58 minutes before being crushed by pressure and heat at depths where pressure exceeded 20 bars and temperature exceeded 150 degrees Celsius. During its descent, it encountered wind speeds of a few hundred kilometers per hour, significant but far less than Neptune's winds. And Jupiter, being much closer to Earth than Neptune, has much shorter communication distances and stronger received signals. So yes, atmospheric probe missions are possible in some environments, but Neptune is more extreme than Venus or Jupiter in crucial ways. The combination of supersonic winds with extreme cold, with great distance from Earth, creates a more difficult challenge than previous missions have faced. And those previous missions were also limited. They survived for less than an hour in the most hostile conditions. They explored only the outer portions of the atmospheres. They didn't penetrate to great depths or survive long enough to study long-term atmospheric dynamics. For Neptune, even these modest achievements would be more difficult to replicate. Now let me discuss the scientific questions that make Neptune's atmosphere interesting, because I think it's worth understanding what we'd hope to learn from an atmospheric mission, even though I'm arguing such missions are essentially impossible. What makes Neptune scientifically valuable? First, Neptune is an ice giant, a category of planet that's common in the galaxy based on exoplanet surveys, but that we understand poorly because we only have two examples in our solar system, Neptune and Uranus, and we've only visited each once, briefly. With Voyager 2, understanding ice giants helps us understand planetary formation and evolution more broadly, helps us interpret observations of exoplanets. Second, Neptune's powerful winds and dynamic atmosphere are puzzling and poorly understood. Why are the winds so fast? How is energy transported from Neptune's interior to its atmosphere? What drives the storms and cloud formations we observe? Answering these questions requires measurements throughout the atmosphere composition, temperature, pressure, wind speeds at various altitudes and latitudes. Third, Neptune's interior structure is unknown. We know there's a rocky core surrounded by a mantle of water, ammonia and methane ices, surrounded by a hydrogen-helium atmosphere, but we don't know the exact proportions or the phase transitions between layers. Atmospheric measurements could constrain models of the interior through observing how pressure and temperature vary with depth, through measuring gravitational anomalies, through detecting seismic waves if they exist. Fourth, Neptune's magnetic field is unusual. It's tilted 47 degrees from Neptune's rotation axis and offset from the planet's centre. Understanding why requires understanding Neptune's interior structure and dynamics, which atmospheric missions could inform. So there are legitimate scientific reasons to want to explore Neptune's atmosphere comprehensively, but wanting to do something and being able to do it are very different. And I think the challenges I've outlined make comprehensive atmospheric exploration essentially impossible with foreseeable technology. We might be able to send a probe that survives for a few hours in the upper atmosphere, that makes limited measurements, that provides some data on composition and upper atmospheric dynamics, that's probably achievable, though expensive and difficult. But deep atmospheric exploration, studying the full vertical structure, observing long-term dynamics, penetrating to regions where exotic ice phases exist, these goals are out of reach. The environment is simply too hostile, the winds too violent, the combination of challenges too severe. Now let me talk about cost, because even if we imagine that survival challenges could be overcome through sufficiently advanced engineering, there's still the question of whether such a mission would be economically feasible. Space missions are expensive, and missions to the outer solar system are particularly expensive because of the long flight times, the large amounts of fuel needed for trajectory corrections and orbital insertion, the communication challenges, the long mission durations requiring staff and facilities for decades. A flagship mission to Neptune with an orbiter and atmospheric probe comparable in capability to the Cassini-Huygens mission to Saturn would probably cost $3, $5 billion in current terms. That's a substantial fraction of NASA's annual planetary science budget, which is roughly $3 billion per year. Funding such a mission requires sustained political and budgetary support over decades, more than a decade for development, more than a decade for flight time, years for data analysis and mission operations. That's a tremendous commitment of resources for a mission that, due to the challenges I've discussed, would likely produce limited data from the atmospheric probe component. The orbiter would be valuable. Certainly remote sensing of Neptune and its moons and rings from orbit would provide tremendous scientific return. But if the atmospheric probe survives only a few hours and explores only the upper atmosphere, is the scientific return worth the additional $1 billion or more that the probe component costs? When you could instead fund multiple missions to other targets, Mars, the outer planet, moons, asteroids, that would provide more certain and more extensive scientific returns. I think the cost-benefit analysis doesn't favour a Neptune atmospheric probe mission given the severe technical challenges and limited likely returns. The resources would be better spent on missions with higher probability of success and greater scientific yield. So economics is yet another barrier, not an absolute barrier, certainly, but a practical barrier that makes Neptune atmospheric missions unlikely to be approved, even if technical solutions to the survival challenges could be found. Let me now talk about one more aspect of this that I think is important, and that's the psychological and cultural dimension of why we're drawn to missions like this, despite their challenges. Because I think there's something deeply appealing about the idea of exploring Neptune, about sending probes into the most extreme environment in the solar system, about pushing the boundaries of what's possible. It appeals to our sense of adventure, to our desire to explore the unknown, to our pride in human technological capability. And these are valuable motivations. They've driven space exploration for decades. They inspire young people to pursue careers in science and engineering. They contribute to human culture's narrative about our place in the cosmos. But I think we also need to be realistic, need to distinguish between what's inspiring and what's achievable, need to recognise when our ambitions exceed what's physically possible or economically sensible. Neptune's atmosphere is hostile beyond what any foreseeable technology can withstand for meaningful durations. The winds are too fast, the pressures too crushing, the cold too extreme, the distances too vast, the challenges too numerous and severe. And I think acknowledging this, accepting that some environments are simply beyond our reach, is not defeatist, it's honest. It's recognising reality rather than indulging in fantasies. And it frees us to focus on what is achievable, on missions that can succeed, on exploration that advances knowledge, rather than pursuing impossible goals that waste resources and ultimately disappoint. We can study Neptune remotely, from orbit, using increasingly sophisticated instruments that observe atmospheric dynamics and composition without entering the atmosphere. We can model Neptune's interior and atmosphere using computers and physics, constrained by remote observations. We can study analogous environments in more accessible locations. Jupiter's atmosphere has some similar features and is easier to reach. And we can wait for technology to advance, recognizing that what's impossible today might become possible in the future if fundamental breakthroughs occur in material science or propulsion or energy generation. But I don't think those breakthroughs are imminent. And I don't think pursuing Neptune atmospheric missions with current technology makes sense, given the severe challenges and low probability of meaningful success. So we'll examine the cascade of failures that would afflict any probe descending into Neptune's atmosphere, the communication challenges across billions of kilometers, the cost-benefit analysis that makes such missions economically questionable, and the psychological appeal of extreme exploration despite its practical impossibility. But I want to explore now some deeper questions about what Neptune's hostile environment tells us about the limits of exploration, about the boundaries of what's accessible to us in the universe, and about how we should think about our relationship with environments that are fundamentally beyond our ability to survive in or meaningfully explore. Because I think Neptune's atmosphere represents a kind of absolute barrier, not a temporary limitation, waiting for better technology, but a fundamental incompatibility between the environment and anything we know how to build or are likely to learn how to build. And recognizing such barriers, understanding where they come from and why they're absolute, is important for thinking clearly about what's possible and where we should direct our exploratory efforts. Let me start by thinking about what makes an environment fundamentally inaccessible rather than just difficult. Throughout human history, we've explored tremendously hostile environments, the deep ocean, Antarctica, the upper atmosphere, space itself. And in each case, we've overcome challenges that initially seemed insurmountable through clever engineering, through new materials, through better understanding of the environments we were entering. The deep ocean seemed inaccessible because of crushing pressure, but we built pressure vessels and submersibles that could withstand thousands of bars and reach the deepest trenches. Antarctica seemed uninhabitable because of extreme cold, but we built insulated structures and developed logistics for supplying bases year-round. Space seemed impossibly hostile because of vacuum and radiation and temperature extremes. But we built spacecraft with life support systems and shielding and thermal control. So there's a natural optimism that suggests any environment can eventually be accessed with sufficient technological development, that barriers are temporary and will fall to human ingenuity given enough time and resources. But I think this optimism is sometimes misplaced. There are environments where the combination of challenges is so severe, where the requirements for survival are so far beyond what materials and engineering can provide, that access is genuinely impossible with any technology based on known physics and chemistry. And I think Neptune's deep atmosphere is one such environment. Let me try to articulate why. The deep ocean is challenging because of pressure, but pressure alone can be managed with thick-walled vessels and careful engineering. The materials exist: steel, titanium, specialized alloys that can withstand the necessary pressures while still being workable and affordable. The ocean is also relatively calm at depth, no violent currents, no extreme temperatures, no chemically aggressive environments in most locations. So whilst deep ocean exploration is difficult, it's not impossible. Antarctica is challenging because of cold, but cold alone can be managed with insulation, with heating, with materials that remain functional at low temperatures. And Antarctica, whilst remote and harsh, is at least on Earth you can resupply by ship or aircraft. You can evacuate in emergencies. You have access to Earth's industrial base for repairs and replacements. Space is challenging because of vacuum and radiation and temperature extremes, but these can be managed with pressure vessels, shielding, thermal control systems, and life support. And crucially, once you've solved the launch problem, getting into orbit, you can operate in space indefinitely with proper design. The ISS has operated continuously for more than 20 years, demonstrating that long-term presence in space is achievable. But Neptune's atmosphere combines challenges in ways that can't be managed simultaneously with known materials and engineering approaches. You need structures that withstand crushing pressure while also being light enough and strong enough to survive supersonic winds, while also functioning at temperatures near absolute zero, while also being chemically resistant to hydrogen, and exotic atmospheric compounds, while also being small and light enough to be deliverable across billions of kilometers, while also having instruments exposed to measure the environment, while also maintaining communication across vast distances with limited power. Each individual challenge might be manageable in isolation, but the combination creates requirements that can't be satisfied simultaneously. There's no material that's strong enough and light enough and flexible enough and temperature tolerant enough. There's no design approach that protects against wind while also protecting against pressure, while also allowing measurements, while also enabling communication. The requirements conflict, creating impossible trade-offs where satisfying one requirement makes others unsatisfiable. And this is what I mean by fundamental inaccessibility. It's not that we need better materials or cleverer engineering, though those would help at the margins. It's that the environment itself is incompatible with physical objects that could function as probes or sensors or exploratory vehicles. The forces are too large, the conditions too extreme, the combinations too severe for anything made of matter, organized according to engineering principles we understand. Now, you might argue that this is defeatist, that I'm giving up too easily, that past predictions of impossibility have often been proven wrong by future innovations. And I want to address this directly, because I think it's an important objection. Yes, many things declared impossible have later been achieved. People said heavier than air flight was impossible until the Wright brothers flew. People said breaking the sound barrier would destroy aircraft until Chuck Yeager did it. People said landing on the moon was science fiction until Apollo succeeded. So there's a reasonable skepticism about claims of impossibility. Haven't we learned that human ingenuity usually finds ways to overcome seemingly insurmountable barriers? But I think there's a crucial distinction between technological impossibilities and fundamental physical impossibilities. The things that were declared impossible and then achieved were never actually prohibited by physics. They were just beyond current technological capabilities at the time they were declared impossible. Flight isn't prohibited by physics. Birds fly. The equations of aerodynamics permit it. It's just a matter of building structures light enough and strong enough with sufficient power. Breaking the sound barrier isn't prohibited by physics. It's just a matter of having engines powerful enough and structures robust enough to handle the aerodynamic forces. Landing on the moon isn't prohibited by physics. It's just a matter of having enough energy and adequate life support and sufficient precision in navigation and control. But some things genuinely are impossible because physics prohibits them. You can't travel faster than light. This isn't a technological limitation, but a fundamental feature of space-time structure. You can't build a perpetual motion machine. This violates thermodynamics, which is as fundamental as physics gets. You can't perfectly predict chaotic systems arbitrarily far into the future. This is limited by sensitive dependence on initial conditions, which is mathematically unavoidable. These are genuine impossibilities, not temporary technological limitations. And I think long-duration survival in Neptune's deep atmosphere falls into this category, not because it violates fundamental physics like faster-than-light travel would, but because the combination of challenges creates requirements that can't be simultaneously satisfied with materials and structures made of atoms and molecules organized according to chemistry and engineering principles we understand. You might achieve short duration survival, a few hours, as I've discussed, but sustained exploration over days or weeks or longer, deep atmospheric access to high pressure regions, comprehensive measurement campaigns, these are genuinely impossible with foreseeable technology because the environment is fundamentally incompatible with engineered systems. Now, I suppose one could imagine technologies so far beyond current capabilities that they seem like magic materials with impossible strength to weight ratios, energy sources providing unlimited power, active systems that can counteract any environmental stress. Science fiction imagines such things regularly: ships with shields that deflect any force, materials that adapt to any condition, technologies that make the impossible routine. But these remain fiction because they require capabilities that we have no idea how to achieve and that might violate fundamental limits. You can't have materials with arbitrary strength and arbitrary lightness. There are quantum mechanical limits to bond strengths, atomic packing limits to densities. You can't have unlimited energy in compact forms. Energy density is limited by mass energy equivalence and by the chemistry or physics of your energy source. You can't have active systems that counteract arbitrary forces indefinitely. This would violate energy conservation and entropy increase. So, whilst I can't prove with absolute certainty that future technology couldn't solve Neptune's atmospheric survival challenges, I think the barriers are fundamental enough that betting against solution is the rational position. The environment is simply too hostile, too far beyond what matter organised into machines can withstand. Let me talk now about what we can learn about Neptune without sending probes into the atmosphere, because I think it's important to recognise that inaccessibility doesn't mean ignorance, that we can understand planetary atmospheres through remote sensing and modelling, even without direct exploration. We've learned tremendous amounts about Neptune from Voyager 2's flyby atmospheric composition, wind speeds, temperature profiles, storm systems, magnetic field structure, ring structure, moon properties. And we continue to learn from Earth-based and space-based telescope observations, tracking storms over time, measuring atmospheric spectroscopy, detecting variations in brightness and colour that tell us about cloud formation and atmospheric dynamics. A future Neptune orbiter mission without an atmospheric probe could revolutionise our understanding through long-term observation, through higher resolution imaging, through measurements at multiple wavelengths and over complete seasonal cycles. Such a mission could map atmospheric composition in 3 dimensions through remote spectroscopy, could track wind patterns over years to understand energy transport, could measure temperature and pressure profiles through radio occultation experiments, could characterise Neptune's interior structure through precise gravity field measurements. All of this without entering the atmosphere, without facing the survival challenges I've described. And we can complement observations with increasingly sophisticated computer models. We can simulate Neptune's atmosphere using the equations of fluid dynamics and thermodynamics, constrained by observations, exploring how different assumptions about interior structure or energy transport or atmospheric chemistry affect the predictions. These models can never be perfect. They're limited by computational power, by incomplete understanding of relevant physics, by uncertainties in initial conditions and boundary conditions, but they can capture essential features, can explain observed phenomena, can make predictions that can be tested against future observations. So the impossibility of atmospheric probe missions doesn't mean Neptune remains mysterious. It means we need to study it differently, through remote observation and modelling rather than through direct measurement. This is less satisfying in some ways. There's something immediate and compelling about direct exploration that modelling can't replicate. But it's still genuine science, still advancing knowledge, still revealing truths about how planets work and how atmospheres behave. And in many ways, remote observation and modelling are more powerful than limited direct measurements would be. A probe surviving a few hours in one location tells you about conditions there and then, but doesn't give you a global picture or long-term dynamics. An orbiter observing for years sees the whole planet evolve over time, sees patterns and variations that single-point measurements would miss. Models constrained by observations can explore conditions throughout the atmosphere, can extrapolate to regions that are inaccessible, can test hypotheses about how different factors affect atmospheric behaviour. So whilst I'm arguing that direct atmospheric exploration is impossible, I'm not arguing that Neptune must remain unknown. We can study it effectively through other means, and we should focus our resources on those approaches rather than on impossible probe missions. Now, let me talk about what Neptune's inaccessibility tells us about the broader universe and our place in it. Because I think Neptune, whilst extreme, is not unique. There are many environments in the universe that are similarly or more hostile, that are similarly beyond our ability to directly explore or survive in. Consider the sun's corona temperatures of millions of degrees, intense radiation, magnetic fields that would tear apart any spacecraft. Consider neutron stars' gravity so intense that approaching the surface would mean tidal forces ripping you apart at the atomic level, magnetic fields, trillions of times Earth's field strength. Consider black hole event horizons once crossed, no escape is possible, and approaching closely enough to study the horizon means experiencing gravitational forces that would destroy any structure. Consider the cores of gas giant planets, pressures of millions of bars, temperatures of tens of thousands of degrees, metallic hydrogen in exotic states, behaving unlike any material we can create on Earth. All of these environments are fundamentally inaccessible to direct exploration. We can observe them remotely, we can study the sun's corona with coronagraphs and extreme UV telescopes, we can detect neutron stars through their radio pulsars and X-ray emissions, we can observe black holes' effects on nearby matter, we can infer gas giant interiors from gravity measurements and theoretical models, but we cannot go there, cannot send probes that survive, cannot measure conditions directly with instruments on site. And I think recognizing this, accepting that vast portions of the universe are observationally accessible but not physically accessible, is important for having realistic expectations about exploration. The universe is mostly inaccessible to us. We're confined to environments that are compatible with structures made of matter, at moderate temperatures and pressures, planetary surfaces, orbital space, the outer layers of atmospheres. The extreme environments, stellar interiors, planetary cores, neutron star surfaces, black hole horizons, even Neptune's deep atmosphere, these are forever beyond our direct reach. We're observers, not participants, in these regimes. We can study them from afar, but we cannot visit them, cannot experience them directly, cannot explore them in the hands-on way that we might prefer. And I think this is a kind of cosmic humility that's worth cultivating. We're not omnipotent explorers capable of going anywhere and studying anything directly. We're limited beings, constrained by our physical nature and by the properties of materials we can work with, confined to a narrow range of conditions where our engineering and our biology can function. Most of the universe is beyond our reach, and that's simply a fact about the universe's structure and our nature within it. But this limitation doesn't prevent understanding. We can still learn about inaccessible environments through observation, through theory, through extrapolation from accessible regimes. We can send light to probe distant objects and analyze the reflected or emitted light to learn about their properties. We can use physics to predict conditions in extreme environments based on fundamental principles. We can test those predictions against observations and refine our models. This is how science works, not through direct experience of everything, but through careful inference from limited direct experience combined with theoretical understanding of how nature operates. So Neptune's inaccessibility is not a unique failure or a temporary limitation. It's an example of a broader truth. Much of the universe is beyond our physical reach, and we must content ourselves with remote study rather than direct exploration. This is not defeatist, it's realistic. And it focuses our efforts appropriately on developing better remote observation capabilities and better theoretical models, rather than on pursuing impossible direct exploration missions. Now let me bring this to a conclusion by returning to the specific question of Neptune's winds and why they make the planet impossible to explore directly. Neptune's winds, sustained supersonic velocities exceeding 2,000 kilometers per hour, create dynamic pressures that, combined with extreme cold and increasing pressure, with depth and great distance from Earth and chemical environments and communication challenges, make survival of any engineered probe impossible for more than a few hours in the upper atmosphere and impossible entirely in the deeper atmosphere. This isn't a temporary technological limitation. This isn't a challenge that better materials or cleverer design will overcome in the near future. This is a fundamental incompatibility between the environment and what engineering can achieve with matter organized into machines. The forces are too large, the conditions too extreme, the combinations of challenges too severe. Materials that could withstand the pressure can't withstand the winds. Structures that could survive the winds can't handle the cold. Systems that could handle the cold can't maintain communication or make measurements. Designs that optimize for one challenge fail catastrophically when faced with others. And so we must accept that Neptune's atmosphere, particularly its deeper regions, is inaccessible to direct exploration with foreseeable technology. We can study the upper atmosphere briefly. A few hours of data from a robust probe is probably achievable. We can study the planet remotely from orbit and from Earth through increasingly sophisticated observations. We can model the atmosphere computationally, testing our models against observations and gaining understanding through theory. But we cannot explore comprehensively, cannot penetrate to great depths, cannot observe long-term dynamics directly, cannot experience the environment in the hands-on way that direct exploration would provide. Neptune remains alien, hostile, incomprehensible in some ways, despite our best efforts to understand it. And I think that's all right. I think accepting that some places are beyond our reach, that some environments are too extreme for our presence, that some phenomena must be studied indirectly rather than experienced directly. This is maturity. This is wisdom. This is recognizing the limits of our capabilities while still valuing the knowledge we can gain within those limits. Neptune's winds will continue to blow at supersonic speeds, will continue to drive storms and shape clouds and transport energy, will continue to create the most violent atmospheric conditions in the solar system. And we will continue to study them from afar, to marvel at their power, to seek understanding of their causes and their effects, to incorporate Neptune into our broader understanding of how planets work and how atmospheres behave. But we will not survive those winds. We will not send probes that endure for extended periods in that environment. We will not conquer Neptune's atmosphere or tame its violence or overcome its hostility through engineering prowess. The winds are too fast, the environment too extreme, the planet too alien for our presence. And that's simply the reality of exploring a universe that contains environments far more hostile than the ones that gave us birth. Environments that exist not for our benefit or our study, but simply because the laws of physics operating on matter under extreme conditions create them. Neptune doesn't care whether we explore it or understand it. The winds blow regardless of our presence or absence, indifferent to our curiosity, unconcerned with our technological capabilities or our scientific ambitions. And I think recognizing this indifference, this fundamental disconnect between what we want and what nature permits, is important for having proper perspective on our place in the universe. We're curious beings who want to explore and understand, but we're also limited beings constrained by physics and chemistry and engineering realities. And when those realities make something impossible, when the environment is simply too hostile for our presence, we need to accept that limitation and work within it, rather than denying it or imagining that determination and ingenuity will overcome fundamental physical barriers. So Neptune's winds remain, in an important sense, unexplored territory. Territory we can observe but not visit, can study but not experience, can model but not measure directly in all their terrible power. And perhaps that's fitting. Perhaps some things should remain wild, untamed, beyond our reach. Perhaps the universe should contain mysteries that resist our attempts at comprehensive understanding, environments that remind us of our limitations, places where nature's power so exceeds our own that we're forced to remain observers rather than participants. Neptune is such a place. Its winds are such a phenomenon. And they will continue to blow long after human civilization has ended, long after Earth itself has become uninhabitable, long after the sun has died and the solar system has gone dark. The winds care nothing for any of this. They simply blow, driven by Neptune's internal heat and the physics of fluid dynamics and the structure of the atmosphere, creating conditions of violence and beauty that we can appreciate from afar but never truly know through direct experience. That's the reality of Neptune. That's the impossibility of survival in 2,000 km/h storms. That's the limit of exploration in a universe that contains places fundamentally incompatible with our presence.